Hello everyone and welcome to the AI Research Roundup. I am Alex, your host. Today is May 9th, 2025. We are looking at a research paper from Hugging Face's trending list published just 4 days ago, titled Optimizing Chain of Thought Reasoners via Gradient Variance Minimization in Rejection Sampling and RL. This paper focuses on making large language models better at chain of thought reasoning, that is, thinking step by step. It identifies a key bottleneck in current training, inefficient estimation of the stochastic gradient, which is like a compass for learning. So this research paper proposes GVM-RAFT, a dynamic strategy to improve this. Alright, so this GVM-RAFT strategy is visually laid out in the first figure. It shows the whole pipeline, starting with a supervised fine-tuning model, or SFT model, an initial version of the large language model. Then it enters GVM iterations. Each iteration has 2 stages. First, an estimation stage for things like accept rates, how often reasoning is good, and Lipschitz coefficients, which are mathematical measures for learning sensitivity. Then, stage 2 assigns the computational budget, ultimately improving the model's policy or its reasoning strategy. Building on that idea of assigning a computational budget, these next plots from Figure 2 illustrate the assigned sample budget in the GVM-RAFT++ approach across 3 different training iterations. We see 3 graphs here. In each, the vertical axis is sample size, essentially how much computational effort is given to a particular reasoning problem, and the horizontal axis is the accepted rate, which indicates how often the model's reasoning for that problem is considered good. Notice how prompts with lower accepted rates, those on the left, generally receive a larger sample size. This really highlights that dynamic allocation strategy at work. Okay, so looking at the actual performance, we see a comparison of different training methods across several mathematical reasoning benchmarks. The methods include the standard reward-ranked fine-tuning, or RAFT, which is an iterative process to improve models by learning from good examples, and another reinforcement learning algorithm, GRPO. The key takeaway here is that the GVM-GRPO and GVM-RAFT++ approaches, using that dynamic sample allocation, consistently outperform the standard RAFT++ and GRPO methods, particularly when you look at the average scores across all 5 benchmarks. This really shows the practical benefits. Following up on those performance improvements, these next 2 plots really visualize the convergence speed. Convergence here means how quickly the model reaches its best performance. We are looking at average accuracy on the vertical axis versus training steps, which are like learning iterations, on the horizontal. The green line, representing GVM-RAFT++, consistently stays above the orange RAFT++ line in both plots. One plot uses a smaller sample size of 8, the other a larger one of 32. This clearly shows GVM-RAFT++ not only reaches higher accuracy, but does so in fewer steps, confirming that faster learning. Alright, so building on that faster learning we saw with GVM reward-ranked fine-tuning++, these next 2 graphs further explore the GVM strategy's versatility. We are again looking at average accuracy versus training steps for 2 model sizes, Quen 2.5 Math, 1.5b, and the larger 7b. Now, alongside reward-ranked fine-tuning++ and GVM reward-ranked fine-tuning++, the authors include GRPO, another type of reinforcement learning algorithm, which is a method where AI learns by getting feedback, like rewards for good answers, and its GVM-enhanced version. The key takeaway is that applying the GVM sample strategy to GRPO shows similar improvements, with GVM-GRPO outperforming standard GRPO. This really underscores the broader applicability of the GVM approach. Indeed, that broader applicability is a key point. So to wrap things up on this insightful work concerning chain of thought reasoners, these are AI models designed to show their step-by-step thinking. The authors tackled a common inefficiency. They introduced a dynamic sample allocation strategy, formerly known as gradient variance minimization. This technique makes the learning process more stable and efficient by reducing variability in the training signals. The result, well, is significantly faster learning and improved accuracy by smartly focusing computational effort. That is all for this AI Research Roundup. Thanks for tuning in.